Dear colleagues, today I was thinking about the brain and I came to the conclusion that brain are much like muscles. Muscles, if you train them, they will become bigger. Of course, it depends on your predisposition, if for your constitution, how are you and how much you can develop. But if you don't train, you won't get muscles. And the same is on the with the brain, except that we don't get bigger or smaller heads. Otherwise, we would immediately see, this one is, I don't know. But we form in our brains connections with neurons and we become smarter. So, if, for example, you are just at home or just playing in casino all day, then you maybe are not developing your brain too much. And if you don't go in the supermarket, you don't know what is happening with X. So in that case, you may miss that X went first 4 times up, 400%, and then they fell down exactly at 87.153% just when a new president arrived. I mean, nobody has ever seen anything like this. It's a superlative achievement, I would say. So today we have a lot to do with the math. I think this one is the last or pre-last lecture, so I won't bother you much more with this. Maybe later we will see how things will develop. And I would say this is from our book, and it's not just my idea. This was also Mark and Bill are together, and as you know, other scientists developed this. We are just presenting things to you. So let us begin. I hope it will be useful, and let's get started. So, in previous lectures, we made some mistakes which I would like to correct right now. And the problem is that I'm working too fast and I'm not focused enough. And also it was a glitch because I think sometimes she likes to see that I make some mistakes which I hope are not critical. So what is about when we have A, B is actually A semicolon B, you get a scalar, and AB is then the same as A dot B, and then you have a tensor AB. Then we have a system, equation of nth order, linear differential equation of nth order, which becomes system of linear differential equation of first order, and there are n plus 1 system of linear order. And it can go in both directions. You can put this there and that this. And finally, we should just write g of xy is 1/3 r squared h minus v, and v is constant, and f was alright. So that's for this. I hope it's clear. And now we will have directional derivative. It's a very useful thing also in economy, for example, to maximizing the profit or minimizing the cost. Then in heat transfer to find direction where you want to watch this, and also many things are things. And what is all about, if you have partial x and partial y, you get just the change of slope in x or y direction. But sometimes you want in direction of some vector u, which must be a unit vector. And unit vector you get simply, if you search unit vector of v times the norm of v, divided by the norm of v. And we can have function f of vector x, or we can even have a vector function y of x, which consists of many functions, f1 to fn transpose. And this will be the first case, and this will be the second case. And you can have also tensor, but I don't know where would you use it. So direction derivative has many notations, and one is nabla, subscript u, f of x, then is the capital D, subscript u, f of x, and then it's also, it's quite a lot of them, nabla, f, x, times u, scalar product, and you can also write partial f of x vector, partial u vector. And more mathematically, this is a limit where alpha goes to 0, and here we have x f of x plus alpha u minus f of x divided by alpha, and finally this is also the same as derivative at alpha is 0, f of x plus alpha u. And this was the first case. In the second case, if you have vector, this is good for solving the system of algebraic nonlinear equations. It's very similar, except that you get here this is then nabla y of x, and we put this in brackets times u, and this, as we learned, is actually the same as a tensor product, and it brings Jacobian, I think, y of x like this. So now I will put it here so you can see. Hope it's alright. And now the Newton-Raphson method we will do for simple one-dimensional case, so x will not be a vector anymore. And we will set u is x minus x0, and when we have a Taylor series, we showed f of x, which can now be written with this, is f of x0 plus u, and this is approximately f of x0 plus the derivative of f of x0 times x minus x0, which is u. And if we equate this with 0, we can get u. And now if x becomes xk plus 1 for computer, and x0 xk, you get xk plus 1 is xk plus u, and u is minus f of x0 divided f derivative of x0. No, xk, excuse me, xk. x0 became xk. Anyway, and with this equation you can solve, for example, polynomial or any polynomial of any order or any nonlinear equation for the first order. an plus a1x plus a0. And finally, I will present, when you do symbolic calculations or anyhow, you can use computers, and MATLAB is a really good program. So as my good friends I would say best friends, are computer scientists, I want to show that I know programming as well. So at the end, I will present you a picture of this program. You can write it by yourself, and you see that you just put a guess, and you put a guess in complex numbers, because zeros can be complex as well. Here you guess, then it makes a tangent, and here you get a new guess, and it's approaching the zero here. So this is how the program works. Hope it will be clear. So thank you for listening, ladies and gentlemen. Have a nice day, and see you soon. One day, Konchi decided that ocean was calling, and so he had embarked on the ultimate adventure, a solo sail around the world. His trusty vessel, the Cosmic Wanderer, was sturdy and adorned with vibrant faded tapestries. His provision was simple: mushrooms for profound contemplation. Konchi meditated, played his worn-out guitar, and occasionally, when the mood struck and the stars aligned, he'd partake in a cosmic voyage. As the hours drifted, a shimmering haze appeared on the horizon. It solidified, resolving into an island, lush and impossibly green, crowned with trees that seemed to glow. But it wasn't the vibrant flora that stole Konchi's breath. It was the figures emerging from the spacecraft that looked as it had come from another planet. Beautiful women glided across the sandy shore. They moved with an ethereal grace, their voices weaving a melody that was utterly captivating. They danced, their movements fluid and hypnotic, beckoning him closer with outstretched hands and beautiful eyes. Konchi found himself scrambling for the boat.
They're calling to me, man, an untouched paradise with pretty ladies from space. True beauty.
Suddenly, a rough hand clapped him on the shoulder.
Konchi, what in the seven seas are you doing?
It was Barnaby, his mate from a passing cargo ship which had spotted Konchi's erratic course, drawn by its peculiar zigzagging. Konchi cried.
Cosmic ladies, man, they're here. They've been waiting for me. I need to join them. We will dance and sing together.
Barnaby squinted at the horizon.
Lad, there's nothing out there but open water. And a mighty strong heat haze, by the looks of it.
He glanced at the scattered mushroom steams on the deck. Konchi, slowly coming back to a less vibrant reality, rubbed his eyes. The shimmering island began to fade, the dancing ladies dissolving like mist. The captivating melody was replaced by the familiar creak of his boat. He realized it was all just a dream.